Hi, everyone. Today, I'm going to talk about Deoptimization, how YJIT speeds up Ruby by slowing down. My name is Kokubun. I work on the YJIT team at Shopify. YJIT team is part of the Ruby infrastructure team. We maintain a lot of Ruby-related open source through time and improve the ecosystem. News is, we're no longer working on YJIT. We are these days working on another music compiler called YJIT. Maxime is going to give a talk about it tomorrow. So if you're interested, go to the talk. But today's topic is still relevant to the YJIT as well. The technique we are going to talk about today is going to be necessary for that YJIT compiler too. So don't worry about it. And another thing is, we are also hiring. It's kind of rare position. If you're interested in working on Ruby open source project full time, the position is open. This QR code is specific to the RubyKaigi attendees. So scan the QR code and apply for it now because the positions are limited. And if it's gone, it's gone. If you also want to work on YJIT, now is the best time because it's not finished yet, so you can build the infrastructure and the core implementations of it. So yeah, let's build YJIT together with us. And I also maintain the latest stable branch of Ruby releases. I just released 3.4.3 this Monday. We also kind of collaborate on backporting things to the Ruby 3.4 branch inside the Ruby infrastructure team. I still maintain the merge of everything, but we share the maintenance of this branch this year. So today's talk is about YJIT. YJIT stands for Yet Another Just-in-Time Compiler. And Just-in-Time Compiler does optimization by switching from the interpreter, which interprets the virtual machine instructions that are specific to the CRuby implementation, to machine code that can be natively executed by Intel or ARM CPU. And the performance today is this is a speed of YJIT.org website, which shows the YJIT performance compared to the interpreter on various benchmarks. And for example, on the Rails bench, which performs the active record queries and do the HTML rendering, it's twice as fast as interpreter today. Even with the I/O, we can do a lot of optimizations on those benchmarks. And this is still benchmarks and not the real world workload, but in the actual production workloads, this is the performance of storefront vendor, which has the highest traffic in our company. And it shows 18% speed up on average and 23% speed up on median. And we also deploy YJIT on the Shopify's largest monolith as well. So it's production-ready YJIT. Production-ready YJIT compiler. And also not only Shopify, but also other companies enable YJIT in production as well. These are just the articles that are written this year, but from last year, years ago, we've seen a lot of other articles that said we enable YJIT in production. So please do that if you haven't. But also, another thing is from Rails 7.2, if you're using Ruby newer than 3.3 or equal to 3.3, it's enabled by default by Rails. So if you upgraded Rails to 7.2 or newer, or Ruby 3.3 or newer, and you switch the defaults to 3.7.2 or newer, then you might be already running YJIT in production without noticing. So, and today's focus is going to be on something called Deoptimization. If you may have attended RubyKaigi before, you might remember this RubyKaigi 2016 talk called Deoptimizing Ruby, done by Shohei. And that was about optimizing Ruby interpreter by doing something called Deoptimization. And that idea was pretty interesting, and it didn't end up being merged to the master branch, but today as of Ruby 3.4 or 3.5, we have some mechanism called deoptimization master branch, and it's already released in 3.3, 3.1, 3.2. Yeah, every YJIT release has the mechanism called deoptimization. So what is it? So what if you can slow down Ruby at any time? You are probably not interested in slowing down the Ruby's performance, but let's say you want to do some optimization, and if you can cancel it at any time, the optimization could be anything. You can do whatever you want and just throw it away if it's necessary. So that way, we can kind of forget about Ruby's dynamic features that prevent Ruby from being faster. So that's something we call as deoptimization. And to kind of give you the hands-on experience, if you are interested, you can try building Ruby with the configure flag code enable YJIT dev. And if you build Ruby that way, the CRuby is going to support the extra command line flag code YJIT which shows the machine code for every single method you have compiled with YJIT. So for example, if you build the Ruby with enable YJIT dev, the -v with --YJIT is going to show plus YJIT dev. It's usually just plus YJIT, but if it's plus YJIT dev, it means it's a development mode of YJIT, so you can show the machine code with a --dump option. And the example is like this. I'm going to talk about this similar code in the next slides, but we just define the method and code it and redefined it, and then shows the machine code that was generated for deoptimization purposes. So I'm going to next talk about traditional YJIT deoptimizations that have existed since Ruby 3.1. So the major thing we do for deoptimization is called code patching. So because we maintain every single bit of machine code we generate, we know exactly which address should be invalidated when we need to do so. So, for example, let's say you have Ruby code like this. You define a constant called foo, and it's 1, and just define a method called lowercase foo, and just refer to the constant. The method foo should return 1. So the YJIT just look at the content of the constant and embeds the actual content of the constant 3. So as you may know, integer is left shifted once, so it's integer 1 is 3 in the machine code. And but if you do this, then the machine code will always return integer 1 from the method foo, but it's not necessarily true if the constant is redefined, because Ruby's constants are just another kind of global variable. It's not actually a constant, and could be redefined at any time. And when it happens, what YJIT does is just patch the code and rewrite to another instruction called jump. And if we do this jump, that could go to anything. For example, the thing we actually do is jump to the trampoline, which jumps to the interpreter, goes back to the interpreter from the JIT code. So by doing this, we can cancel the optimization of inlining the content of foo constant, and then goes back to the interpreter when it executes this method again. And I also like to introduce another deoptimization called global invalidation. So this is another Ruby code I want you to think about what it returns. Raise your hand if you think this is not going to return 1. You win. So, of course, it's going to return 5,000 trillion because it's Ruby. So there's thousands of features that break this kind of optimization in Ruby. And this example has the trace point. In particular, it's a line trace point. So if you define the line trace point event, when you execute another line, you hook the execution of the Ruby and do anything there. So in this example, when you call the number method, after executing the one equals one, then it's going to rerun the block of the trace point, and it sets the local variable again to 5,000 trillion. So of course, it's going to return the number we generated in the trace point. And when we do that, because trace point messes up everything, we just throw away everything. So like this example shows like, it's not the Ruby code we just showed, but it's just on the other benchmark. And like when trace point line event is enabled, we just generate thousands of jump instructions to the side exit code to the interpreter. So yeah, this is what happens if you use line trace point. So today's takeaway is like, don't use line trace point in production. So these are the existing traditional deoptimizations we had in YJIT for years. But I'm also going to talk about new deoptimizations that we added to Ruby 3.4. So the first thing I want to talk about is the invalidation of escape locals. So this is another example. Obviously, it's going to return 5,000 trillion. I'm not going to use trace point, but can you guess what kind of Ruby features you could use in the do something? So somebody called binding, but yeah, it is. So like, not just the binding of the current frame, but any random Ruby method could look at the caller frame, arbitrary caller frame, using the public, like official C API we provide for messing up the Ruby. You can look at the caller frame and then mess up the frame, basically. So whenever you call some arbitrary method that's not in line to your JIT code, it could just mess up the Ruby local variable. So it's not guaranteed that the Ruby local variables are not going to be modified by the callee methods, even if you are not passing the block to the callee method. And with that, we introduced a new optimization called local variable register allocation to Ruby 3.4. We used to just write to memory, like in Ruby 3.3, we were writing only to the memory when we need to deal with the Ruby locals, but from 3.4, we use registers as if it were the regular compiler. And of course, we are going to throw away the code when the binding is fetched by any like callee or wherever. So another example is I want to talk about is called invalidation on Singleton classes. So it's another optimization we added to 3.4. So in this example, the example method defines the string local variable and then concatenate another string returned from the define method, that's bar. So if you don't specify the true to the flag, then it's going to concatenate empty string and bar, so it's going to return bar. And the next step is going to set true to the flag, so it redefines the string plus method on that specific string object. So instead of concatenating empty string and the bar, it's going to just return the foo string literal. So if you run this script with the interpreter, the correct result is going to be print bar first and then foo next. But if you think about how to compile this in YJIT, as of evaluating the receiver of the plus instruction, the string is pushed to the virtual stack. And then as of that, because it's initialized by the string literal, of course it's going to be bare string. Nothing happens to the string yet, even if the flag is true. So because the string is pushed to the virtual stack before executing the define method, the JIT compiler thinks it's going to be the bare string. And after pushing that to the stack, it's going to call the define method. And because the flag is true, it redefines the string plus method on that particular object. So it swaps the class field of the object to the Singleton class that has the special method definition. And after doing so, because JIT thinks it's a string, it may think you don't need to check if it's actually a string. So if we don't do anything with it, it could be just like return bar, because we skipped the redefinition and we already compiled, assuming that the string class is going to be the actual string class. So this is a miscompilation that could happen if you don't invite it on the Singleton classes. So what we do today with Ruby 3.4 is that when Singleton classes are created on particular classes, we track, for example, like string, array, and hash. For those objects, we check if any Singleton class is created for those classes, and if it's any Singleton class for those classes, we just skip the, elide the type check for those classes and invite it when the string Singleton class is defined. The next thing I want to talk about is lazy frame push. So with this example, we have the string, empty string, and set byte 0, just letter A. And because the empty string doesn't have any length, you can't set the character to the index 0 because the length is 0. So it should raise the exception like index 0 out of string. But the YJIT optimizes this string setByte method. So we could make it behave like this. So if you don't have any invalidation, YJIT could just skip pushing the frame for the setByte and just inline the optimized instructions for the setByte implementation. And then if you do that, even if the argument is invalid and should raise error, because we haven't pushed the method frame for the setByte, the behavior could be the lower one, which doesn't say string setByte in the stack trace. So it's the wrong behavior. The thing we introduced to Ruby 3.4 is the lazy frame push. If you when the setByte sees the invite argument, it internally calls the CB API that allocates a new exception object. And when we reach the C function that allocates the exception object, it calls back the YJIT hook that checks if it has registered the invalidation for that program location. And if it's already registered, then we lazy push a frame to the stack when necessary. And the way it works is we have, this is the first time showing the Rust code in the RubyKaigi, but it's looks at the hash table that has the program counters as keys. Program counter is like one-to-one mapping to the program specific location, and the values are the something that we need for pushing the frame, basically. It has the location of the receiver on the stack, and also has the method entry so that we can materialize the method the frame content. And the trick is because any method could be executed from a same location. For example, even if you call the setByte method, depending on the receiver of the object, the setByte could be something different. For example, you can redefine the setByte for string, or any other receiver could be used. So the program counter is not necessarily tied to a specific method entry. So because we kind of assume that the setByte is not going to be polymorphic call, we assume that it's a one-to-one mapping, and if it's not, we can just exit to the interpreter when that happens. So that way we can calculate the frame content we need to push lazily based on the program counter, which we have to set for other reasons, like tracing and side exits. And so we set the program counter anyway, so we use that for materializing the frame later. The next thing I'm going to talk about is the YJIT-only Ruby methods. So as you may know, Ruby is faster than C, so we have method definitions like this for array each. So this is the historical C implementation for array each. We attempted to just replace that with Ruby-based array each, which we didn't end up doing, but in the micro benchmark, the Ruby version of the array each was actually faster, even on the interpreter. But if you run the benchmark, large enough benchmark, then it actually performed worse, which is why we are now thinking of doing the switching between the C and the Ruby version. So with YJIT, because going to Ruby to C and then going back to JIT from the C world is actually slow. So we don't want to do the boundary crossing, especially the C to Ruby is a bad thing. So to avoid that, if you define array each in C, then you must cross the boundary from C to Ruby because the block is often just defined by Ruby. So we shouldn't define array each in Ruby if you want to make that not happen. So this is the complicated code we write. That's actually shipped in the Ruby 3.4. So it's actually not really deoptimization, but achieves the same kind of purpose. So what it does is it checks if the core array each C implementation has been redefined, and if it's not redefined, then move on to execute those content, and just undefine the C-based implementation of array each first, and then redefine the Ruby-based array each. So, and the thing I want to talk about is this one. So this is new in Ruby 3.4, and it's called C trace attribute. And this primitive ATTR exclamation is the special syntax that's specific to the CRuby internal core classes that were developed by Koichi before. And this is not a method call, but it's just parsed by Prism and then compiled into special binary that's only possible inside the CRuby core classes. And if you have the ctrace attribute, this method entry is going to have the flag called ctrace. And if it does have the ctrace flag, what that is, so this is the original behavior of the exception raised inside the block of the given to array each. So if you raise something inside the block given to array each, the backtrace, of course, should have the array each entry. And the interesting part is, because array each is defined in C in this example, it shows the file name called -e, which is the -e given to the Ruby command. However, what happens if we redefine that in Ruby is usually like this. So the lower one is the version that defines array each in Ruby. So when we re-implement something in Ruby, the backtrace has the Ruby file name. I mean, it's actually not the file name, just its internal array for core classes defined in Ruby, but the file name is going to be different. For some reason, C methods just look at the caller flames location and shows -e, which is not actually the location that defined the array written in C, but anyway, if it's rewritten in Ruby, this is going to be different. But this is something we don't want to happen because if this happens, we redefine. So if you enable YJIT, because of the with YJIT helper, we swaps the implementation of the array each only if the YJIT is enabled. So what happens in real world is if you you enable YJIT, suddenly your test cases that match the backtrace is going to break. Like, for some reason, people like to test backtraces, so these tests are going to break just because you enable YJIT. So we don't want that to happen. So like, to prevent that, we added the ctrace attribute, and that's what we do for fixing or dealing with this problem. So like, the switch from the C, like -E to the internal array happens all the time when you upgrade the Ruby minor versions, because minor versions should have backward incompatibilities. But switching in between the interpreter and YJIT should be as smooth as possible. So the ctrace attribute is what we have for fixing that problem. I talk about it a bit fast, but that now comes to conclusion. So the deoptimization enables speculative optimization with like lazy, inviting, throwing away the code later. And Ruby 3.4 optimizes, YJIT optimizes the local variables and method codes using the technique called deoptimization, which is the conclusion of today. Thank you for coming to the talk.